On this video, we're going to talk a very specific type of covalent bonding called coordination bonds or dative bonds. Coordination chemistry, you will see it referred in a different way in different books. So far, we have discussed that when you have a covalent bonding, you have a sharing of electrons. So you have two atoms, more, but to have one bond, you have two atoms, and each of them shares one electron and makes a bond, and they might share another electron and make another bond, and they may share another electron and make another bond. But the basis is that they have one electron each. So if we go back to one of the examples we used before, you have the hydrogen that has one electron in the outer shell, chlorine, that can share one electron in the outer shell, and they make a bond, HCl. However, you can have a specific type of covalent bond, which is what we call coordination bond, in which what you have is one atom will have the electrons and the other atom will have empty orbitals. So what you get is an atom that has electrons that can be shared, that finds another atom that has orbitals that are empty and not very high of energy, so not very far from the nucleus, that can accept those electrons. So the bond is made again by two electrons, but one of them will put the electrons in the mix and the other one will have an orbital which is low in energy enough to accept those electrons. I've used very specifically the letter M to show what that atom that accepts electrons looks like, because they are metal ions. Metal ions, and especially transition metals, so the D part of the periodic table, the ones in the center, are very good at making this type of coordination bonds. You've got metal ions that have these D orbitals, which are relatively low in energy, relatively close to the nucleus, that can accept electrons. They just don't have any, but they have all these empty orbitals that could in theory be used. When they find an species, another compound, it could be an anion, but it could also be a neutral species, that has electrons to donate, then they both can make a bond. We call those species, those compounds, it could be a compound, a neutral compound, a neutral molecule. It could also be an anion, something with a negative charge. They have electrons to donate and they can attach to the metal ion, and we call that a ligand. So you have the metal ion, which is the one that accepts the electrons, and the ligands that donate the electrons. And ligands can be anions, for example. So for example, you could have a chloride anion or a fluoride anion, donating electrons, or you could have an organic molecule, or you could have a neutral species. For example, you could have H2O, the molecule of water, or the molecule of ammonia. And if you remember from a previous slide, when I was drawing the molecule of water, I drew this. I told you, yes, it has this V shape because there are the two bonds with the hydrogens that you can see, but it also has those electrons that are in the outer shell that are not being used for anything, but they are there. Well, if you have a metal ion so a metal but with a positive charge, then you can totally use it for something. You can use it to make a bond. The same with the molecule of ammonia. I drew it in a previous slide, and I told you, look, it has this shape because there are two electrons here in the outer shell of nitrogen that are not being used for the bond. They're just there doing nothing. So that nitrogen has electrons to donate. So if it finds a metal ion, the transition metal ion that has d orbitals that are empty, there of reasonably low energy, is able to make a bond. And that is not it's a specific type of covalent bond, because it's not about sharing electrons, it's about sharing an empty orbital and an electron pair. So each of them put something different to the mix. We talked about coordination number, which is how many atoms are attached to that metal ion. So you can have 1, 2, 3, 4, 5, 6, etc. Some atoms can have some interesting coordination numbers. The most typical ones are 4 and 6. So 4 atoms attached to that central metal ion, or 6 atoms attached to that central metal ion. And this is some typical geometries. For example, if you have two donor atoms attached to the central metal ion, or two molecules, they tend to position themselves as far away as possible, because you've got this, for example, here you've got this, the complex with silver and 2 ammonia molecules, you've got the silver in the middle, and then you have with 1 positive charge, you've got the nitrogen from one of the ammonia atoms donating those electrons. You have the nitrogen from the other ammonia molecule, and well, I mean, the nitrogen comes with the 3 hydrogens. They occupy a space. They physically need the space to settle themselves, so they try to put themselves as far away as possible. When you have 4 donor atoms, then they either pick up, a square planar, and or they pick up a tetrahedral structure and octahedral. If you have 6 donor atoms, for example, you have there a copper with 2 positive charges surrounded by 6 molecules of water, that would be, I'm going to draw only 1. Then the best possible structure is to put themselves in the corners of an octahedron.